All right, guys, nice to see everybody back. And we got 6 more weeks to go, all right, for the course. Lots of good stuff to come. Biggest reminder, your programming test number 1 will be on Thursday during the lecture time in WSC, William Small Center. And to make it up, there's a makeup lecture which I got a survey on the e-class, so please fill it out if you want to express your preference. If you guys really are okay with a pre-recorded lecture, I'm okay with it. I just personally prefer in-person lecture. But if you guys prefer a pre-recorded lecture, be my guest. I'll make them available to you. All right, please fill it out the survey before it's closed. Your assignment number 3 will be released next week on schedule. That one is going to be about link trees. So this assignment number 3 and the following assignment number 4, we're going to put together recursion, trees, and singly linked lists all together into assignments, right? It's going to be a very nice learning opportunity for you to put everything together. Going to be challenging, but very rewarding learning experience. Yeah, you can look forward to it. And your written test, also the guide will be released as well, maybe sometime next week when it's ready. I'll also give you guys some example questions. Okay, you can also look forward to it. Just for this week, if you got some last minute question for me about the programming test, you can feel free. It's tomorrow 3 p.m. You can still feel free to come 1 hour. Okay. Any question about the course before I move on? Alrighty, let's do a very quick recap about what we said before the reading week. So we basically finish off the discussion about singly linked lists. Specifically, we talk about how you can insert into the middle. And the dominating step is really to figure out the so-called previous reference. If you actually want to remove the node, if you want to add a node at index I, then you need to figure out what's really at index I minus 1. And that one there is going to be the dominating step, taking a linear time, right? Just remember. This will be some very valuable information for you to review for the written test, okay? And then we spoke about how you can remove the end of the list. Remove last is an expensive operation for singly linked lists, which will take linear time because you only got a reference to the tail. You don't really have the reference to the second last node. We don't have that. But in the doubly linked list, we do have it, right? So just notice that difference there. And then we spoke about these 2 exercises conceptually. Also, we visualized the steps, how you can insert after and also insert before. I really encourage you to really try. So these little operations that we discussed in the class, individually, they're simple, I agree. However, for the algorithm that you will be required to implement either in your little projects or in the programming test, they have to consist of such simple operation to put them together, right? So they are important building blocks for you. All right, so that's the table that we did about comparing the array and the singly linked list. You can refer to the detail, right, in the recording, right? I mean, not repeat, right here. But we're going to see another table before we get back to the tree. Well, not get back, and before we start talking about the trees. And we introduced the idea about doubly linked lists. I just want to get back to this summary over here, just to remind you. So there are basically 2 extensions we're introducing to doubly linked list and doubly linked node. At the node level, we are introducing this previous reference, and that one there is going to make operation like a remove last much more efficient. Rather than linear time in the singly linked list, it's going to be constant time because now we got a previous reference to get to the second last node, right? Just remember that. And the second extension is by having the header and trailer, these so-called sentinel nodes or guard nodes. So these 2 nodes are really there, storing nothing useful, but if they are standing there so that we can improve the code structure. If you recall, so there were 2 important helper methods that we spoke about before the reading week. One of them is called add between. The other one is called remove, right? So these 2 are the important helper methods you want to keep in mind. So any methods that you want to implement for doubly linked lists, if that has the insertion nature, you should really use the add between. If it has the removal nature, you should really call the remove as a helper method, right? It's just going to make your code much cleaner. You don't really have to repeat the same kind of pointer or references manipulation over and over. Just call the helper method. It's going to do the thing for you correctly. Right, so the exercises for you guys will be things like this, right? You got to trace the code. I also posted on the lecture site some solution video about these exercises. You can review them. Maybe not so urgent for the programming test 1 happening on Thursday, to be very honest with you, but you may want to do that for your written test. That'll be a very valuable review for you. Okay. All right, that's about what we spoke about before the reading week. Any question? So there's one last thing I would like to do before we say goodbye to the linear data structure, which is to do another comparison table. Okay, let's take a look. Right here. So this will be the final table that's going to summarize all the 3 linear data structure you guys have learned so far, right? So this part here, just about the array and singly linked list. Okay, let me just box it, just to make it more explicit for you. This is something we discussed earlier in the lecture about singly linked lists. So for this part here, I may not repeat. You guys can actually look at the previous lecture to see the detail. So this part here, I'll just say see earlier discussion. What I want to briefly talk about are these entries for doubly linked lists, right? That's something we introduced on Thursday before the reading week. Okay, let's start with this row over here. So we talk about basically the size and also the first and the last. We're basically applying the same strategy called trading space for time. We're basically introducing some attributes that we can access with the constant time, so we don't have to implement the algorithm to really take the linear time. So in the case of a doubly linked list, we have the size attributes, and we got header, we got trailer. So how do we get to the first element from the header? Header.getNext. How do you get to the last element from the trailer? Trailer.getPrevious, right? So it's a constant time. So for these operations, it will be big O of 1. And then let's say here, if you want to, let's say this one here, let's take a look. This one here is about element at index I. This one is interesting. It depends on what I is. If I is very, very close to the beginning, in which case you can use next reference to get to there, very cheap. If I is very, very close to the end, then you can use the previous reference. But what if I is very close around the middle of the chain? In that case, it will take about n divided by 2. Next or previous references. So you're not really improving asymptotically. N divided by 2 will be still big O of n, right? It's a very important insight to see here. Even though we got a previous reference, but we're not really improving about getting to the middle of the doubly linked list, okay? So this will be big O of n, especially, for example, when n is very close to, when I is very close to n divided by 2. Okay, I'll make a note here for you. Right? Asymptotically, it will still be linear. Right, the next one here, you can see I want to talk about remove last. Okay, that's really the highlights. Okay, so if I highlight remove last element here, we know that for singly linked list is going to be big O of n, linear time, because we have to somehow get to the second last node, which will take linear time. That's for singly linked list. But in the case of doubly linked list, we got a previous reference. We can simply say trailer.getPrevious, which will give you the last node, and then .getPrevious, which will give you the second last node. So that one there is actually going to be big O of 1, right? So that's something you want to watch out for, right? So for this one here, it's going to be big O of 1, right? So that's really the highlights. So finally, we can also see if you're trying to add or remove, but you're not really given that particular reference, you're only given the index. It's like accessing in the middle. So it will still be big O of n for a doubly linked list. Okay. It's a very quick review about the different operations, how they compare for doubly linked lists. So when you study for the written test or for the exam, I would suggest use this table here as a guidance about the various operations. For each operation, try to think about how the different linear data structure is going to perform. Right? It's very important. Okay? You can expect some question from there to ask about your insights about these structures for the written test. All right, any question? All right, very good. Okay. And then we're now done with basically the linear data structure. We're now moving on to a new lecture. Okay. I think most likely I'll give you guys pre-recorded lecture. That seems to be the overwhelming preference by you guys, which is okay, right? I'll definitely do that. And as I promised, the pre-recorded lecture I'm gonna give to you is pretty good quality. So you can just focus on your learning. So I think for the non-linear data structure I'm going to introduce, I'm not going to give you the video to watch. I'll rather give you some simple contents to watch. So in the lecture, we still discuss the more tricky concept. I think it's going to be better for you. So you can still interact with me, ask me questions. But I'll reach out to you about everything. All right, so now I'm going to switch to the slides, which is already on the lecture site. Okay, let me give you a quick roadmap about how we're going to proceed with this. Trees is a very big topic that we're going to discuss thoroughly in this course, in the second half of the course. As I mentioned in the beginning, when I talk about the syllabus, we don't really talk about graph in this course. So graph will be the focus for 3101, the follow-up course to this. But in this course, we're going to talk about tree. Okay. Let's see very quickly about the topics that we're going to cover, at least. So for trees, I got 3 different lectures to cover. Okay. Oh, of course, I spelled it wrong. There we go. Okay, trees. Okay, the first topic will be about general trees, which we'll see today. And I will talk about what general really means, okay, later. And second one will be more like a special kind of tree, not really general, called binary trees. And we sometimes abbreviate it as BTs, binary trees. All right, the third topic will be binary search trees. Search trees, BSTs. And the next one will be balanced BSTs. BSTs. Okay, number 5, we're going to talk about something called abstract data type. It will be part of your pre-recorded lecture to see what abstract data type is, which is a very simple definition. So you will see that. But for now, we're going to learn something called priority queues. It's more like an application. Okay, we'll get there when we need to. And then number 6 will be a special kind of a balanced binary search tree. Well, sorry, a kind of special kind of a balanced tree. It's called heap. Okay, the last one will be something called heap sort, all right, which we heard about the term for many times, but we haven't done it yet. But that will have to wait before we lay all the groundwork over here. In order for you to understand heap sort completely, you have to understand from 1 to 6, okay? So roughly speaking, this part here will be part A, and this will be part B, and then this will be part C, roughly. Okay, that's what we're going to cover. And we have to understand about different properties. What does it really mean to be binary? And what does it really mean to really have the search property for the binary trees? What does it really mean for your binary search tree to be balanced? And also, what does it really mean to have a tree that can satisfy the heap property, right? So these are all the properties that we have to learn, their mathematical definitions and properties, right? Which we're going to have some discussion in class. All right, that's the roadmap. And today, we're going to start with general tree. And of course, another aspect will be for all these, well, especially for these two. We're going to see how we can do Java implementation, which you will do for your assignments, right? You also got a chance to practice the theory, okay? Which is also important. So let's now start with the slides and see what we should talk about here. So we're going to understand about linear data structure versus nonlinear. I'm going to revisit the concept once more, okay? And then we're going to talk about the terminology for general trees. And we'll only get to binary trees next Tuesday, okay? But today, general trees, a little bit lighter than next Tuesday. And then we can see how we can implement a generic tree, which will be important for your assignment number 3 and 4. And also mathematical properties for binary trees, especially how you can analyze the heights of the tree. That has to do with the performance of the algorithm. And also how we can traverse the tree, how you can systematically visit every node or every place in the tree so that you can complete certain algorithm. So once we complete the discussion about tree traversal, you'll find that any algorithm we kind of solve in this course over here has certain flavor about visiting using the tree traversal algorithm, which we'll see. Okay, either Tuesday next week or Thursday for sure. So you will just learn about it in time for your assignments. All right, general trees. Okay. Let's now revisit very quickly about linear data structure. And trees that we're going to talk about is nonlinear. But let's just visualize, again, how we distinguish between them. In order for a data structure to be linear, that means we have the notion about predecessor and successor. What I missed in the slide, which I can fix later, is when I say predecessor and successor here, they should be unique predecessor or unique successor. Uniqueness property is very important. Okay, let's take a look. So let me just go here, right here. All right. So here I kind of put all the structure that we're going to learn in this course somehow in a single page. So you can see this is the array, this is the singly linked list, and this is doubly linked list. So all these are the linear data structure. And what we're going to see from today will be the non-linear, like a tree. And this tree here happens to be a binary tree because you can see from each place you branch out 2 times. From this one here, you branch out 2 times. From this here, you branch out 2 times, etc. It's a binary tree. I just choose one example. Let's now revisit about why we say this is linear, this is also linear, and this is also linear. Let's see. Okay. Let's start with maybe singly linked list. Okay. The essence about it is you actually got some, let's say if I got a node here in the middle. Okay. The only way for me to move forward is by following the next reference right here, right? And I said the node I'm following the next reference to is called my successor. And this is a unique successor. There's only one successor I can get to. Okay, so we say that this is using next to access the unique successor. Right, that one's obvious. Unique, very important, right? Let me highlight it. Unique successor. What about doubly linked list? Well, not only that you got unique successor, you also got unique predecessor, right? So if you look at, for example, over here, let's say I'm talking about this node in the middle, right here, all right? So I got a unique successor for that by following the next reference right here. That's a unique successor. I can also follow the unique predecessor using the previous link, right? Unique successor, unique predecessor. Okay, let me write it down. So this will be the unique predecessor. And using the next link over here, that will be the unique successor. All right, what about array? Similar idea, but it's just that we don't have the next or previous reference. What we have is just indexing, right? So let's make it a little bit more general. Let's say I'm somewhere in the middle, right? If this is index I have also a unique successor at index I plus 1, obviously, right? And then unique predecessor at index I minus 1, right? So think about I plus 1 will be the index of the unique successor. And also I minus 1 over here will be the index of the unique predecessor. Right? Let me emphasize again, unique is really important. All right, unique. All right, that's a quick summary about why all the data structure we have learned so far are linear. And let's now talk about nonlinear, which we're going to see many examples to come. Let's start with the very first one. Okay, one thing you got to understand is the way we understand tree in the context of programming or CS or software engineering, right? So in real life, tree kind of grow bottom up from the ground, but in our context, tree kind of grow top down. All right, you got to keep that in mind. Kind of weird, but we got to stick to it. So we call the very top place or the node the root. And there's nothing else above if you say this is already the root. Okay? And then we said that this structure here is so-called hierarchical structure. Okay, I'll write it down. It's a hierarchical structure. Hierarchical structures. And one very familiar example to all of you will be back in 2030. If you remember, we learned about inheritance, right? So whenever you have one class extends another class, you're basically building like an inheritance hierarchy. If you look at the inheritance hierarchy for Java collection library, maybe for smartphone, etc., you will see a tree, basically, right? It's just one example. Now we're going to see other examples as well. And what's really special about hierarchical structure is you can somehow divide the different nodes in the tree into levels. Okay? I'll elaborate a little bit more about what I really mean by levels. It has to do with definition for depth and height, which I'll get to around the end of today. But let's now see some intuition, okay, levels. So let's say we start with the root. Okay? We call the root level 0. So I'm going to draw a line right here. So level 0 contains just one node, always, just the root, nothing else. So I would say L0 for level 0. Okay? I'll elaborate exactly how we can understand the level a little bit more. Okay? And then you can see from this root here, it will simply branch out. Whenever it branch out, it's going to go to the next level, right? So this is going to be level 1, right? And for every node in level 0, so for every node in level 1, it's going to reach out to level 2. So we got 1, 2, 3, 4 nodes, right? And etc. As you can see, the number of nodes is simply going to grow, potentially exponentially, right? Down to the bottom. But how exactly it will grow exponentially, we're going to see some mathematical property, maybe on Tuesday. But for now, you don't need to worry too much. Okay, okay, level 2. And then here, this will be bottom level. Okay, I'm just going to use a special line here. So this will be level 3. That's the bottom level. Somehow, the number of the bottom level signals like how high the tree is. And how high the tree is also tells you if your algorithm somehow start from the root of the tree, how many links would it take you to really get to that bottom level? So that number there is going to impact the running time for your algorithm. I'm being a little bit vague over here, but we're going to see precisely what I meant a little bit later. I want to give you some intuition. Okay. All right. Let's see if I missed anything. Okay, so one more thing. So if you look at this, why is that nonlinear? If you look at the root over here, you can see we branch out into either this one here or this one here. So the number of successors is not just one. It's not unique. So we got multiple successors. So that's why it's not linear anymore. It's nonlinear. So I'm just going to write over here, okay, for those two branches, so you got multiple successors. Multiple, not unique. Of the root. And one more thing to say. Think about how you will implement this nonlinear data structure in Java, right? I'll just give you a little bit preview, okay? Imagine that, of course, every node in the tree, let's say the root, it definitely is going to store some data, like an element, like a string or integer. We can make it generic, number one. Number two, if I want to branch out, in general, you may branch out for 3 nodes here. You might branch out for 4 nodes over here. So you cannot just say, I'm going to have first child, second child, third child, and fourth child. You simply don't know how many variables you need for that particular node class. So the way to store all the, we call the children of this particular node is by using some linear data structure, like an array or simply linked list, which you will see in assignment number 3. Okay, I'm going to write it down here. So when we say multiple successors of the root, okay, in programming, they are stored in a linear data structure. For example, singly linked list. So the example code I'm going to give you to you guys for discussion in the class is going to be array, which is linear. But when you actually look at the assignment problems next week, it's going to be singly linked list, which you are also familiar with, right? You can post some additional challenge for you to really think through about what we have learned so far. Okay? So for this comment here, if you're not exactly getting it, that's okay. Once you see a little bit Java code today and maybe next time, I think you appreciate that a little bit more. Okay. All right, any question so far? All right. So, question, yeah. Jennifer.
So I want to clarify something. When you were
of course.
talking about the predecessors and
yes.
stuff, the singly linked list would also have a predecessor, even if it has no way to go back, right?
Typically, okay, I see what you mean. In the singly linked list, you might, okay, I see what you mean. You might say, for example, Mark here, let's say Mark here. We wouldn't say Alan is a predecessor because there's no way for Mark to get to Alan. unless you write some loop to get to it, right? So here, when we say predecessor, successor, assuming that you have access to it. But,
Like directly, like instantaneously?
yeah, exactly, directly, yeah. So for Mark over here, you can directly go to its successor with no cost, well, without minimum cost. And let's say with Mark over here, you can also go to either Alan or Tom with also constant cost by calculating indices. And for here, for this node here, you can also go to either here or here with no cost. Well, again, minimum cost, right?
So long as you have either a unique successor or a unique predecessor?
Yeah. Oh, okay. Good question here. Okay, that's very good question. Here, okay, let's look at this node here. This node here has two successors, so it cannot be linear because it doesn't have a unique successors. What I didn't say was, which we're going to see. If you see this node, if I want to go upwards, there is only one way for me to go upward. So if you think about predecessor for this node here, this is a unique one. But we wouldn't call this linear because the fact that it got two branches out for the successor already violates the linear property. So we cannot call it linear. Okay? I can write it down. So you can think about for this particular node right here, it has a link right here. You can think about that one is a unique predecessor. But since we already got multiple successor, that's already a violation for linear property. So we wouldn't say tree is a linear structure, right?
Yeah, I'm just saying because the definition says you need both, right?
Sorry?
The definition says you need both.
The definition says if you do have either predecessor, well, the definition says the follows. If you have predecessor, it got to be unique.
Oh.
If you have access to successor, it also got to be unique.
Okay.
If that's not unique, you violate either one of them, it's not linear anymore.
Okay, makes
Yeah,
sense.
good. Yeah, good to clarify. Alrighty, so we're done with this. Let's see what's left on the slides. All right, I think you guys can take a look. I think just to repeat what I just said, you can see in the textual form. And now, for now, until most of the lecture for today, we're going to see some terminology for the tree. Okay. Again, don't worry too much about ADT. That's going to be covered in the makeup lecture. It's a very simple concept. I wouldn't get to it just yet. Okay, today. So we're going to see terminology for trees, and we're going to see some simple ones, and we're going to see some very fundamental ones for you to think recursively about tree. Okay, towards the end. But you'll see many terms we're going to see kind of borrow the idea from family trees in reality. You're going to see things like root, which you already saw. You're going to see parents, siblings, and children. Also, you're going to see ancestor and descendants, right? Ancestor descendants might sound familiar to you for those of you who took 2030 with me, right? The same definition, but we're going to see. All right. Let's now go over one by one. And I think the way we're going to go, the slide contains both the definition and example. So what I will do is I'm going to use the same running example for all the concept. So it's a reasonably complicated family tree for us to really dive into to explain the concept. But in the slide, I'll just go over some definition quickly on the slide, and then we'll see how to visualize them on the iPad. I think that'll be the best way for you to grasp the idea. None of them is difficult, right? Very straightforward. So the root first. We got root, we got parents, and also we got children, right? Let's start with the root. The root is basically the top element of the tree, just the top, okay? Okay, for this family tree here, the root is David. And I'm just going to highlight it and say some property here. So this is the root, the top. And the root is always unique for the tree, of the tree. And then we also got the concept about parents. So parents is basically the immediately above node. Okay, for example, if I am looking at Ernesto, what will be the node immediately above Ernesto? David, right? By following this link over here. And what about Elsa? Parents will be following immediately above will be quiz, right? It's pretty easy. Okay, so I'll just make one example here. So you would say, for example, Elsa will be the parents of both Shirley, Vanessa, and also Peter, all three of them. Shirley, Vanessa, and also Peter. Right? That's about parents. And children is just symmetric idea. Children will be all the nodes immediately below that particular node, right? Just symmetric. For example, when I say here, Shirley, Vanessa, Peter, all they share the same parents, Elsa. Symmetrically, we'll say all three of them are the children of Elsa. Okay, right here. So we got Shirley, Vanessa, Peter here. So these are the children of Elsa. All right. So we talk about the root, we talk about parents, we talk about children. Okay. Can you see something very special about the root? Somehow. Root is basically the only node that has no parents. Agree? Because you cannot follow any link up. It's already the root. Okay? So this one here is going to be the only node that has no parents. But if you're doing in Java, the parents attribute is going to be null. Parent. All right. Another thing you can also see over here is we call these, well, we're going to see later, they are called the external nodes or leaves, which I'll define a little bit later. Okay. So these nodes, like Shirley, Vanessa, and Peter, they happen to be at the bottom of the tree. They are the nodes that have no children. Right? You can see the top here is the node that has no parents. And the nodes at the bottom are the nodes with no children. Right? Kind of symmetric. Okay? The nodes without children. Of course, Ernesto here also has no children, right? Just to make sure you don't miss that. All right, so let's now move on. And then we got, okay, that's good. All right, any questions so far about the concept? Yeah, Josh.
All the childless nodes like leaves?
Yeah, well, for example, let's say, yeah, so for any node without any children, yes, which we're going to see, we're going to introduce a little bit later. So for nodes such as Ernesto, Shirley, Vanessa, and Peter, so these nodes have no children. We call them leaves of the tree. Yes, we're going to see that. Either call them leaves or external nodes. Okay, we'll get there. Okay. All right, there's another interesting concept over here called sibling. Okay, sibling simply means the nodes that share the same parents. For example, you can see Shirley, Vanessa, and Peter, they share the same parent, Elsa, so they are siblings. These three nodes are siblings. Okay? All right, let's now talk about another two concepts, ancestor and descendants, right here. And to really talk about them, let me just make a new page to talk about them. Oh, another thing to say, you can see for siblings, they are at the same level. Right? For example, you can see Ernesto and Elsa, they're at different level. There's no way they're siblings, right? Let's now talk about ancestor and descendants. Okay, I just got this new page over here, right? That's clean. And let's now talk about ancestor and descendants. Okay. First of all, let's now see the definition. Okay, ancestor will just be, well, if I talk about ancestor, the ancestor of some node n. Right? Any node can have ancestor. Okay? By definition, it's going to be the node itself. Okay? Always include the node. And also the node's parents, the node's grandparents, parents' parents. And also all the way to the root. That's a definition for ancestor. Okay? For example, if you look at Shirley over here, how many ancestors does Shirley have by the definition? 4. Okay, good. Not 3. Shirley herself all the way to the root right here. You basically go from Shirley and follow the parent link, go to Elsa, follow the parent link to Chris, follow the parent link to David. All the nodes covered are the ancestor. All right? And we say that the path for you to go from Shirley all the way to David is the ancestor path for Shirley. Okay? Let's now write it down. So we got Shirley, let me just use this one here. Okay, we got Shirley here. And then we follow the link for parents, we go to Elsa. And then we follow the parent link, we go to Chris. And then we follow the parent link, we go to David. And of course, once we get to David, his parent is simply null, so we cannot follow any longer. So you can also imagine if you want to somehow give it a node, you want to figure out its ancestor path. How would you do it, either recursively or iteratively, right? You can think about that, right? It can be computed either way. So we say that this is the ancestor path for Shirley. Let me write it down here. So the whole thing is called the ancestor path of Shirley. And you can write it this way. You can say I start from Shirley, and then I go to Elsa, and then I go to Chris, and then I go to David. Right? You can see this is the node n that we're talking about, and the David is the root where we stop about the ancestor path. Right? Go all the way there. Okay? And the ancestor path will always be unique for any node. It's not possible for Shirley to get to the root by the different path. Not possible, because the parents are unique, so the path must be unique. So I'm going to say ancestor path over here is guaranteed to be unique. Guaranteed. Okay, ancestor path right here. It is unique. Because the parents is unique. All right, good. Okay, very good. Okay, we talk about ancestor. Let's talk about descendants. Okay. Descendants is kind of the opposite way. Okay. The descendants will simply be children, grandchildren, great-grandchildren, all the way down to the bottom of the tree, where you cannot get any deeper, basically. All right. So that will be called a descendants. And don't forget, for n's descendants, you got to include n node itself. Okay. So let's say, for example, let's do 2 examples here. 3, how about that? What would be the descendants? Oh, you know what? Let me put it a little bit more systematically for you. Okay. Let's say I got some node over here for me to consider. What about the descendants for Vanessa? How many? 1. Vanessa, right? Thank you. Okay, what about, let's say, another one. What about descendants for Elsa? How many? 4, okay? It's going to be Elsa herself, also Shirley, Vanessa, and Peter. Okay, one more. Which node has the most number of descendants? The root, obviously, right? Because root, every node is underneath it. All right? And then I'll say David over here. Then I will say all nodes in the tree. All right, very important. Okay. Yeah, we got ancestor, we got descendants. Okay. And one more remark, which I didn't mention. Okay, a node is both its ancestor and descendant at the same time, according to our definition, which is okay, right? We just be consistent with our definition. A node is both its ancestor and descendants. All right, that's good. Okay, and let's see the next concept. Okay. Yeah, and if I'm going too fast, please do slow me down. Otherwise, I'll just keep going. Okay. All right, so we got ancestor, descendants. The next one will be something called siblings. I think sibling we talk about already, so we're good. Okay, sharing the same parents. And subtree, all right? Guys, if you have not been paying attention, this will be the concept to pay attention. Subtree, all right? Subtree is the most fundamental concept for you to define recursive algorithm on your tree. Because if you recall the general pattern for recursion, we say that if you're given a problem that's too big for you to solve, what do? Reduce the size of the problem. In the case of the array, we consider like an index I+1 array. If you got array list, you can maybe say, I get rid of the first element, I consider the rest of the array list. What about tree, right? I'll just draw very quickly, right? But I'm going to be more elaborate as we go over the concept. Let's say for this, I want you to calculate the size of the whole tree. This problem here is way too big for you to solve right away. According to the pattern, what we do is, okay, I know that this tree here, the root itself is David. That should be counted as 1. And then I would say, okay, I know that because tree is a recursive concept. I will go to the first child, Ernesto, and look at all the nodes underneath it, like a descendants. That will be like a subtree, it's called. What's its size? And then I will look at the second child over here and look at recursively what's the size of this particular subtree. I got another answer. And then I simply add this, and this together recursively. All right? Oh, you should have let me know earlier. Okay, let me do it again. Okay, sure. If I'm given this tree over here to calculate its size, okay? Guys, next time, please don't be shy. Just shout to me, all right? I need that. I want to calculate the size of this tree here. Way too big for me to calculate, okay? So what I do is, I know that the root is David. That one should be counted as 1, for sure. And then I will try to recursively do 2 things. Number 1, child number 1, the first child. I'm going to calculate how many nodes are there for this child's descendants. And then recursively calculate what's the number of nodes under this child as well. I will get answer number 1, answer number 2. I can add up all these 3 numbers. That's how I solve it recursively. But we're going to see more precisely how to do it. I'll write it down for you and do some tracing a little bit later. But I just got to remember the subtree here we're going to see is a very important concept for you to master. Okay? When you want to do recursion on the tree, it's all about subtree. The definition, as I mentioned, is all about descendants, right? So whenever you want to talk about subtree, you always want to contextualize what is the root of that particular subtree. It is important. If you simply say, I consider this particular subtree, I'll ask you, what's the root of that subtree, right? It's important to know. All right, let's now do several examples over here. Okay. Let's now talk about subtree. Okay. Let me now start with the smallest subtree you can get into. Basically, a node that has no children is the smallest subtree you can have, being its root. Okay. So I'll give you one example here. Let's say Peter over here. Peter has no children just by itself, right? And the descendants of Peter is just Peter himself, okay? So this is the subtree, or smallest subtree. The smallest subtree rooted at Peter. Smallest in the sense that it contains just one single node, just Peter himself, because he has no further children underneath it. All right, there's another subtree here. For example, let's say the subtree rooted at Elsa, right here. Okay, so this is the subtree rooted at Elsa. Rooted at Elsa. A simple question. What will be the largest subtree? Rooted at David, right? Just the original tree containing every node, because the root contains descendants every node. All right, very good. Okay, it's not a difficult concept, but you can see the subtree can be as small as like this, which would be the base cases for your recursive algorithm. But when you actually start with something that's not exactly the base case, you got to further divide and conquer about subproblems, right? That's something you will see more and more, okay? All right, let me just annotate the last one here. So we got David here, okay? This will be the biggest subtree that's rooted at the absolute root of the original tree. So this will be the largest subtree whose root is the absolute root of the tree, right? That's about subtree. Are we okay with this? Okay, we're going to go deeper and deeper about the subtree, right? We're just going to go gradually, all right? And let's now consider a problem which we'll try to solve recursively, okay? Let me now write down the problem, and then I'll let you guys to think, I'll just tell you the solution right away. That might be a little bit better, okay? We shouldn't expect you to really come up with any recursive algorithm on the tree just yet. But I'll guide you through. Oh, there we go. Awesome. Let me now write down the problem. The problem is, given a node, return the size of the subtree given a node n. Return the size of subtree rooted at n. There might be a different way to ask this question here. I might say, given the node n, tell me how many descendants you got. It's the same question, basically, right? Because subtree is really has to do with the descendants, right? The same question. So I'll just write down for you. So the size of the subtree is really about the number of descendants. The same question, really. Right? So this problem here, we're going to see how we can solve it recursively. But I'm not going to do any Java code or any pseudocode over here. I just want to show to you on the tree itself how you can think about it recursively right away to see the tracing. I think that might be more beneficial at this stage. Okay? So first of all, understand what the problem is. Okay? So one example let's say call this method here or routine, count. So for example, if I say count, let's say I pass the node David. What value should it return? Well, it should return 1, 2, 3, 4, 5, 6, 7, 8, right? Another example, if I say count, if I say Chris, right? It should be 1, 2, 3, 4, 5, 6. Okay, one more. If I say count, let's say Shirley, that should be just 1, right? And etc. So now the question is, how do we solve this one recursively, right? We want to see that recursive, like a tracing, right? So what's going to happen is like this, okay? So we start with count of David. This is how we start with, right? So typically, another thing to really compare and contrast. If you remember in your assignment number 2 and in the practice number 1, for the singly linked list problem, usually the input is simply a single node. And we say that node is pointing to the beginning of some chain of nodes, right? Similarly, whenever you're given any problem about trees, you will also be given a single node. And that node is pointing to the root of the tree. So similar idea. So in the singly linked list, it's pointing to the beginning of the chain. In the case of tree, it's pointing to the root of the tree, right? A single node. So now we start with count David, right? So we start with here. However, David is actually the root of a very big tree, which I cannot solve right away. So the idea would be David himself should be counted as 1. I'll put 1 here. And then I want to recursively count the subtree rooted at David's first child, which I'm going to write here. So this one here is going to be basically count Ernesto. And this one basically is about recursively count the size of subtree rooted at the first child of David. Right? We're given David here, and we're getting the first child of David and figure out its subtree. So you can think about this subtree here is a subproblem. But we're lucky because this subtree here has one node. That's the base case. If the subtree contains just one node, how many nodes does it contain? Well, of course, one. So this one here, you can imagine this will be the base case, returning 1 right away. Returning 1 right away. So it's a return value, so I'm going to say 1 here, right? So we're good so far. And of course, we are not done yet. In order to calculate the size of the tree, we want to know recursively this one we know is 1, and also the node itself, and also recursively calculate the size of the subtree rooted at David's second child. All right, this is something we're going to trace a little bit further. So what I will do is I'm going to draw this subtree right here. And for this part over here, we're actually going to have count quiz. All right, again, it's going to be the number of nodes in the subtree rooted at David, which is the input, second child. Okay, so far so good? Okay. So this one already done, so we got to go further for this. In order to count quiz, what should we do? Right? That one is all too big, the tree. It's not base case. So what we do is we're going to do like this. Quiz himself is going to be counted as 1. And then I need to recursively count first child subtree, which will be, which will be right here. I got it wrong. Elsa Shirley, right here. So this will be count Elsa. And the second child is Anna. This will be count Anna. Can I follow? Right? So in order to count the number of nodes of the subtree rooted at quiz himself should be 1. And then the first child of quiz, the subtree here, should be counted recursively, which will be done. And also the second child over here is also need to be calculated recursively. But this one here is already the base case. So we know that it's going to return 1. So this one here is going to be 1, which I know that it's going to be returned, so 1 here. Okay, we also got 1 here, right? Okay. All right, we're almost done. And then when you want to count Elsa right here, also too big, not base case. What do we do? Well, again, you're trying to say, so maybe for, I'm running out of color, basically. Okay, how about blue? Okay, so for Elsa over here, herself should be counted as 1. And then she got 3 children. Each one of them should be counted recursively for the subtree, right? So here we got 1 here, which will be count Shirley. And this one will be to count Vanessa. And this one here will be count Peter. Each one of them, I know that it's going to return 1 because they are the base cases. Okay, we are kind of halfway. We're basically reaching the base cases, and now we haven't really figured out the total answer just yet. Let's see how the recursive call are going to return, and we're going to combine all the answers together. That's really important. Okay, so let's now do the final stage. So now thinking this way. So in order to count Elsa, we already know it's 1, 1, and 1, and then plus 1, right? So we got a 3, we got a 1 plus 1 plus 1 from the recursive call plus the 1 of the root itself. So we got 4. So that means for alpha, count alpha over here is going to return 4. All right, for this particular subtree. And then we're now able to count quiz. In order to count quiz, we need to count alpha, which we know is 4. So 4 plus 1 plus 1. We got 6, right? So that one there is going to give us 6. So for count quiz, it's going to give us 4 plus 1 plus 1, right? You can see the 4 comes from here, this subtree here, and the 1 is the quiz himself, and also the 1 comes from the subtree here, right? So we got 6. All right, we're almost done. So 6 over here. So finally, how do we figure out count David? Right, we're gonna get a result for count Ernesto, which is 1, and for count quiz is 6. 6 plus 1 plus 1, we got 8, which is exactly the answer, right? All right, so that's a final answer. And the way I trace it is just how the recursive method is gonna work, right? Let me recap very quickly, and then I'll take questions if you have any. The way to think about this question really is, the input is really supposed to be the root of the tree, for which you want to calculate how many nodes are there. To start with the root over here is way too big, the problem. So we count the node itself as 1, and then try to figure out recursively, let's say it only has 2 children, right? In that case, we got first child has a subtree, figure out how many nodes are there. Second child over here also has a subtree, figure out recursively how many nodes are there. Once we got the answer, we can simply add them up all together. So what you got to do is try to see if you can reproduce this kind of tracing for the problem you're going to solve. That's something you will need. All right? Any question about this? Okay, calculating the size is a very basic problem. If you remember, when we introduced you about singly linked lists, we also try to calculate the size of the chain, right? So now we're showing you how you can calculate the size of the tree. But this one can definitely be done recursively. Okay, let me write one more comment for you. The subtrees are really the sub-problems for you to make recursive calls on. Subtrees are the sub-problems for you to make recursive call on. Okay, so we're really talking about sub-problems, okay, about subtree right here. Okay, good. All right, any questions? We good? Okay. All right, let's now move on. Okay, I think that's really good. Can we just do one more, and then we can take a, let's do 2 more, and then we'll take a very short break. Okay, 2 more. Very quick. Right? I think this might be the trickiest part I want to talk about today, right? About calculating subtree and make some connection to recursion. But we're going to see many reinforcement about this kind of concept. Let me do one more page, and then I want to give you guys some question here. The same tree, but now the question is, how many subtrees are there in total? How many subtrees are there in total? How many? Diego, go first.
The same number of nodes in the tree.
Aha, okay, maybe the same for you, right? Okay, whenever I ask you about how many subtrees in total, it's a no-brainer question. You just calculate how many nodes are there in the subtree. Because by definition, each node in the tree can be the root of its own subtree. All right? 8. Very good. And then I will give you some follow-up. So it will be 8, which is the number of nodes in the tree. However, in the written test, I might give you a simple question like that, but I may ask you in a slightly more complicated way, but I will show you to you. One possibility could be, I'll suggest you try this table here. I'll try to fill it out partially for you. Make a table here, and then 2 columns. So one would be about the size of the subtree. And then how many subtree of that particular size? For example, if I say how many subtrees are there of size 1? How many? How many subtrees are there of size 1? 5? Okay, good. 1, 2, 3, 4, and 5, right? Basically, all the nodes without any children, if they are the root of the subtree has only size 1, right? So I'm just going to put 5 here, but I already explained to you which 5. And of course, you can do some kind of numeration over here. What will be the largest size possible for subtree for this particular tree? Number of nodes, right? Just 8, containing all the nodes, okay? So you're going to go all the way to maybe just 8 right here, and then we only got 1. This one I can annotate here. This will be rooted at David. And you can figure out about what about size 2? What about size 3? What about size 4? Some of them could be just 0. There's no subtree of this particular size, right? You can fill out the table, okay? That might be more or less what I want you to compute precisely and ask you certain ones, in the test, okay? Okay, one more, and then we'll take a very short break. One more, which is just about some simple concept which are important. Let me do this, and then we can take a very short break. Okay, so next two will be about external nodes and also internal nodes, which Josh just talked about earlier, maybe about 20 minutes ago, but let's now define them. External nodes or leaves are basically the nodes without any children, all right? That one's easy to see, but let me just annotate them. So we got basically 5 of them. We got Ernesto right here. And also we got Anna. And also we got Shirley. We got Vanessa. And we got Peter, right? We got 5 of them. So these are so-called external nodes. So these are external nodes, and then sometimes we also call them the leaves of the tree. And other nodes that are not leaves are so-called internal nodes. So David here has some children. Chris as well has some children. And Elsa also has at least one child, right? So these are called the internal nodes. One here, one here. Internal nodes. And for those of you who might be in CS major and you're studying EECS 2001, if you have already learned about context-free grammar, you talk about parse tree, right? So internal nodes are something called non-terminals. And for leaves or external node, they're called terminals, in case you're studying that. If not, don't worry, okay? And let me say one more thing, and we take a break. It is very important for you to make such distinction between the kinds of nodes we are having, internal versus external. Because for external nodes, once you reach some external nodes, you know that your algorithm should really start returning. You should really start returning, otherwise you will go indefinitely. So leaves are usually the base cases. On the other hand, for internal nodes, since you know that the internal node has at least one more child for you to explore further about whatever you want to do for the algorithm, so they are not terminating, so they are the recursive case. Okay? Recursive cases. Like how we count the size of the tree. All right. Any questions? Yeah, go ahead.
Is there any difference between the leaves that are at different levels? Like, for example...
Okay, I see what you mean. I would say, well, so of course, there are different ways to really categorize the nodes. One aspect will be about levels, in which case you would say this leaf, yes, it's actually in level 1, and these leaves are at level 2. I would say just different aspect, really. You wouldn't really compare, let's say, this leaf against these leaves, really. Just different aspect to categorize them. Yeah. Mm-hmm. They're not really related concepts, so you don't need to worry. Yeah. All right, why don't we take a short break by taking attendance for 3 minutes? Okay, already. Okay, so let's see. We got a few more concepts that we can finish today, and then we're good. Okay. So let's now talk about. Okay, we talk about internal, external. Okay, we're gonna talk about edge, path, and also depth, and also heights. So these are the 4. Okay, let's talk about one by one. Edge is very straightforward. Just a pair of parent and child nodes. Just 2 nodes basically. Okay. One example will be, you can see here, I got this particular parent link between Ernesto and David, right? So I can say this is one edge where I got the child over here and I got the parents over here. So the pair, David and also Ernesto, is an edge, right? So this is what we call an edge. Okay, a path is really something we have seen earlier, right? But I can just do one more time. It's really just about like a sequence of nodes that somehow is connected by the parent link. So here, I got one here, one here. So basically, answers the path from Vanessa all the way to the root. So this is one path. And let me just write it down. We got Vanessa, we got Elsa, we got Chris, we got David, right? You can think about there are 3 edges in this particular path. Edge number 1, edge number 2, edge number 3, right? So we can think about Vanessa, Elsa is one edge. And then Elsa and Chris is the second edge. And then Chris and David is the third edge. Right? We got 3 edges. All right, easy. Okay. And I want to spend the remaining time maybe talk about depth and height. Okay, which is important. Depth and height. Okay. Again, let me copy this and then we're going to do that. Okay. So let me just do it here. Let's talk about depth first. Okay. It's very important to really talk about these 2 concepts over here, but they are very closely related, but they might also be confused very often. Okay. Whenever we talk about depth, it should be a depth of a particular node. Of a node. It will be the number of edges by definition, the number of edges or the number of parent links from a particular node. So let's say node n, from n to the root. For example, for Vanessa, it takes 1, 2, and 3 links to the root. So the depth should be 3. For Elsa, the depth should be 1 less because it takes 1 and 2 links. And now, based on the depth of the nodes, we can divide the tree into levels. So that's something I said I'm going to elaborate. The way you divide the tree into level is by the depth of the nodes. So every level has the nodes with the same depth, basically. So what I would do is I'm just going to do this. Okay, I'm going to divide the tree into one level here, and also one level here, and also one level here. Okay, this level here is kind of special, the first level. The depth will just be 0. How many edges would it take for David to go to himself? 0. So depth should be 0. And then every node in this level here is going to take 1 link to go to the root. So the depth should be 1. And also every node in this level here is going to take 1 and also 2 into the root. So the depth should be 2. Finally, every node in this level here is going to take, for example, 1, 2, and 3, and also 1, 2, and 3, and also 1, 2, and 3. So the depth should be 3. All right? That's how you should understand depth conceptually. But we're going to see next Tuesday to see how to compute it conceptually. All right? But let me see how much time I got. I got 3 minutes, enough time. Okay? The second concept is something called height. Of a tree. All right, notice that we don't really say the height of a node, we say height of a tree. Okay? The definition is it will be the maximum depth of descendants of its root. All right, by definition. Okay? I'm just going to use 2 minutes to illustrate this to you by 2 examples, right? Oh, sorry. Let's now do that in 2 minutes. I'm going to put one here, and I'm going to put another one here. Okay, the same tree. However, whenever you want to calculate the heights, you don't necessarily always have to calculate the tree rooted at the root. Okay, so what I mean is, if I choose over here, David, versus if I choose Elsa right here, I can have 2 different problems over here to solve. Okay, so for the first one, I might say what would be the heights of the tree rooted at David. And also, I'm going to say over here, what will be the heights of the tree rooted at Elsa. Okay, let's just do one together, right? The other one, I can go over the answer with you, but you can also try. Let's do one. Let's say for this one here, right? The way to do it is, by definition, we want to calculate the depth for all the descendants, right? So I would say you do the following, okay? So start with the root. D should be equal to 0. You want to go to the next level, D should be just 1. Next level, D should be equal to 2. Next level, D should be equal to 3. Once you're done with this, what's the maximum depth? 3. So the height will just be 3. All right? I got 30 seconds. Let me finish the second one. All right, guys, bear with me. How do I calculate the heights for this particular subtree, right? Again, let's annotate. I got D will be equal to 0, starting from here. That's the root. Be careful. And then I got D equal to 1, D equal to 1, and D equal to 1. So what will be the heights of the subtree here? 1. So now, let me make a final remark. Whenever you want to calculate height, know where the root is and calculate the depth value accordingly and find the maximum. We're going to see on Tuesday how you can do that recursively. And I'll see every one of you on Thursday. All right?